Hello everyone, and welcome. Today, we're going to hold a review session to consolidate our understanding of some of the most powerful tools in differential calculus. We'll be focusing on the applications of differentiation. By the end of today's class, you will be able to use the first and second derivatives to fully analyze the behavior of a function. Specifically, we'll start with a quick refresher on our core differentiation rules. Then, we'll dive deep into the meaning of the second derivative, using it to understand a function's shape, or concavity. We'll learn how to find points of inflection, which are points where the shape changes. And finally, we'll use the powerful second derivative test to quickly classify local maximums and minimums. This is a comprehensive toolkit for curve sketching and optimization. Alright, let's begin with a quick recap of the rules we use to differentiate more complex functions. These are our foundational tools. First up, the chain rule. We use the chain rule when we have a composite function, which is essentially a function inside of another function. The rule states that if y is a function of u, and u is a function of x, then the derivative of y with respect to x is the derivative of the outer function with respect to its argument, multiplied by the derivative of the inner function. In other words, dy is a phi to dx equals dy is u times du slash dx. Let's see this in action. Consider the function. Y equals the quantity x squared plus 5, all raised to the power of 4. Here, the inner function is the part inside the parentheses, and the outer function is the power of 4. So, we can set u equal to x squared plus 5. This simplifies our expression for y to just u to the 4th power. Now we find the derivatives of these two separate parts. The derivative of u with respect to x, du by dx, is simply 2x. The derivative of y with respect to u, dy by du, is 4u cubed. Finally, we apply the chain rule by multiplying these two results together. So dy by dx equals dy by du times du by dx, which is 4u cubed times 2x. Our last step is to substitute the expression for u back in, so our final answer is in terms of x. Substituting x squared plus 5 back in for u, we get 4 times the quantity x squared plus 5 cubed, all times 2x. Simplifying gives us 8x times the quantity x squared plus 5 cubed. Excellent. Now what if we're multiplying two functions of x? For that, we need the product rule. If a function y is the product of two other functions, u and v, its derivative is the first function times the derivative of the second, plus the second function times the derivative of the first. That's u times dv slash dx plus v times du dx. Let's take an example. Let's find the derivative of y equals x cubed times cosine of x. We'll identify our two functions. U is x cubed and v is cosine of x. The derivative of u is 3x squared, and the derivative of v, which is cos of x, is negative sine of x. Now we just plug these pieces into the product rule formula. We have u times dv slash dx, which is x cubed, times negative sine of x, plus v times du by dx, which is cosine of x, times 3x squared. Cleaning that up, our final derivative is negative x cubed sine of x plus 3x squared cosine of x. It's a straightforward application of the formula. And that brings us to our third rule for when we are dividing functions. This is the quotient rule. For a function y that has a ratio of u over v, the derivative is the bottom function times the derivative of the top, minus the top function times the derivative of the bottom, all divided by the bottom function squared. A common way to remember this is low d high minus high d low over the square of what's below. Let's work through one last example for these rules. Let's differentiate y equals e to the x divided by x squared. Our top function, u, is e to the x. Our bottom function, v, is x squared. The derivative of u, e to the x, is just e to the x. The derivative of v, x squared, is 2x. Now, we carefully substitute these into the quotient rule formula. We have v times du by dx, which is x squared times e to the x, minus u times d, v slash d, x, which is e to the x, times 2x. And this is all over v squared, which is x squared, squared. Simplifying the expression, we can factor out an x e to the x from the numerator, giving us x e to the x times the quantity x minus 2, all over x to the 4th. We can cancel an x, leaving our final answer as e to the x times the quantity x minus 2, all divided by x cubed. So, those are our 3 fundamental rules for handling more complex functions. Make sure you are comfortable with them, as everything we do next builds upon them. Now that we've refreshed our memory on how to find derivatives, let's talk about what the times second time derivative tells us. This is where we start to really understand the geometry of a function's graph. The second derivative, which we write as f double prime of x, is simply the derivative of the first derivative. While the first derivative, f prime of x, tells us the slope or the rate of change of the function, the second derivative tells us the rate of change of the slope. In other words, it tells us how the slope itself is changing. So f prime of x gives us the slope of the function, and f double prime of x tells us how that slope is changing. This concept is called concavity. There are 2 types of concavity. First, we have concave up. This is when the graph of the function is shaped like a cup or a U. If you look at the tangent lines along a concave up curve, you'll see their slopes are increasing. They go from negative to 0 to positive. Since the slope is increasing, its rate of change, the second derivative, must be positive. So, a function is concave up where f double prime of x is greater than 0. The other type is concave down. This is when the graph is shaped like a frown or an upside down U. Here, the slopes of the tangent lines are decreasing. They go from positive to 0 to negative. Since the slope is decreasing, its rate of change, the second derivative, must be negative. So a function is concave down where f double prime of x is less than 0. Let's find the intervals of concavity for a sample function. Let's analyze the function f of x equals x cubed minus 6x squared plus 5. To find the concavity, we need the second derivative. So, first, we find the first derivative. The first derivative, f prime of x, is 3x squared minus 12x. Now, we differentiate again to get the second derivative. The second derivative, f double prime of x, is 6x minus 12. The concavity can only change where the second derivative is 0 or undefined. In this case, it's a polynomial, so it's never undefined. Let's find where it's 0. We set f double prime of x equal to 0, so 6x minus 12 equals 0, which gives us x equals 2. This is our potential point of change in concavity. Now we test the sign of f double prime of x on either side of x equals 2. Let's pick a test value less than 2, like x equals 0. Plugging this into our second derivative, we get f double prime of 0 is negative 12, which is less than 0. This means the function is concave down for all x less than 2. Now let's pick a value greater than 2, like x equals 3. F double prime of 3 is 6, which is positive. This means the function is concave up for all x greater than 2. So we can conclude that our function is concave down on the interval from negative infinity to 2, and concave up on the interval from 2 to infinity. In that last example, we saw that the concavity of the function changed at x equals 2. This special type of point has a name. It's called a point of inflection. A point of inflection is a point on a curve at which the concavity changes from up to down or from down to up. For a point to be a point of inflection, 2 conditions must be met. First, the second derivative at that point must be 0 or undefined. Second, and this is crucial, the sign of the second derivative must actually change as we pass through that point. The concavity must flip. It's very important to remember that f double prime of c equals 0 is a necessary condition, but it is not sufficient. You must always test to see if the concavity changes. Let's look at a classic counterexample. Consider the function f of x equals x to the fourth. Let's find the second derivative. The first derivative is 4x cubed. The second derivative is 12x squared. Now let's find where the second derivative is 0. Setting 12x squared equal to 0 gives us x equals 0, so x equals 0 is a candidate for an inflection point. But now we must check the second condition. Does the concavity change? Let's test a point to the left of 0, like x equals negative 1. F double prime of negative 1 is 12, which is positive, so it's concave up. Now let's test a point to the right, like x equals 1. F double prime of 1 is also 12, which is positive. It's also concave up. Notice that the concavity did not change. It was concave up on both sides of x equals 0. Because the concavity does not change, x equals 0 is not a point of inflection for f of x equals x to the fourth, even though the second derivative is 0 there. This is a critical distinction to make. Going back to our previous example, f of x equals x cubed minus 6x squared plus 5, we found that at x equals 2, the second derivative was 0, and the concavity changed from down to up. Therefore, that function has a point of inflection at x equals 2. Alright, we've seen how the second derivative describes the shape of a graph. Now let's use it for one of its most common applications, finding and classifying local maximum and minimum points. This is called the second derivative test. First, let's recall what a local maximum or minimum is. These are the peaks and valleys of our graph. They occur at stationary points, which are points where the first derivative is 0. So at any local maximum or minimum, the slope of the tangent line is horizontal, meaning f prime of x equals 0. The second derivative test gives us a quick way to determine if a stationary point is a maximum, a minimum, or neither by looking at the concavity at that point. Here's how the test works. Suppose we have found a point x equals a where the first derivative is 0. First, if the second derivative at that point, f double prime of a, is positive, what does that tell us? It means the function is concave up at that point. The concave up shape looks like a valley. Therefore, the point must be a local minimum. Second, if the second derivative at that point, f double prime of a, is negative, that means the function is concave down. A concave down shape looks like a hill. Therefore, the point must be a local maximum. And third, if the second derivative at that point is 0, the test provides no information. It's inconclusive. The point could be a maximum, a minimum, or an inflection point. In this case, you would have to go back and use the first derivative test, which involves checking the sign of f prime of x on either side of the point. Let's apply this test to our running example. Let's find and classify the stationary points of f of x equals x cubed minus 6x squared plus 5. Step 1 is to find the stationary points by setting the first derivative to 0. We already found the first derivative is 3x squared minus 12x. Setting this to 0, we can factor out 3x. To get 3x times the quantity x minus 4 equals 0. This gives us two stationary points, x equals 0 and x equals 4. Oops, let me correct that. The derivative of minus 6x squared is minus 12x. So f dash of x equals 3x caret 2 to 12x. Factoring gives 3x of x4 equals 0. So the stationary points are x equals 0 and x equals 4. Let me recheck my previous work. I see. In the concavity example, I used f of x equals x caret 3 to 3x squared plus 5. Let's stick with that one to be consistent. My apologies. Let's use f of x equals x caret 3 to 3 x squared plus 5. Okay, let's restart the example with the correct function, f of x equals x cubed minus 3x squared plus 5. The first derivative is 3x squared minus 6x. Setting that to 0, we get 3x times x minus 2 equals 0. Our stationary points are x equals 0 and x equals 2. Now step 2 is to use the second derivative to classify them. We already found the second derivative for this function earlier. Our second derivative is f double prime of x equals 6x minus 6. Now we evaluate the second derivative at each stationary point. First, for x equals 0, f double prime of 0 is 6 times 0 minus 6, which is negative 6. Since the second derivative is negative, the function is concave down, and x equals 0 is a local maximum. Next, for x equals 2, f double prime of 2 is 6 times 2 minus 6, which is positive 6. Since the second derivative is positive, the function is concave up, and x equals 2 is a local minimum. And there we have it. We found and classified the stationary points without having to test intervals on the first derivative. It's a very efficient method when it works. To wrap up, let's quickly summarize what we've covered today and talk about why it's so important. We've built a complete toolkit for analyzing the behavior of functions. We started with a review of the essential differentiation rules, the chain, product, and quotient rules. These are the building blocks for everything else. These rules allow us to find the derivative of almost any function we encounter. Then, we moved on to the second derivative. We learned that the sign of the second derivative tells us about the function's concavity. A positive second derivative means the function is concave up, like a valley, and a negative second derivative means it's concave down, like a hill. We define points of inflection as the specific points where the concavity changes, which can happen only when the second derivative is 0 or undefined. And finally, we put it all together in the second derivative test, a powerful shortcut for classifying stationary points as local maxima or minima. The final point on our checklist was about using calculus to find optimal solutions. This is the real-world application of finding maxima and minima. Whether you want to maximize profit, minimize material usage, or find the most efficient route, you are doing an optimization problem. The techniques we've reviewed today are the mathematical foundation for solving those problems. Finding the best solution to a problem is often a matter of finding a maximum or a minimum value of a function. By understanding these concepts, you can not only sketch a detailed graph of a function, but also model and solve real-world problems. Thank you for your attention today.